So welcome to part 2 of this engine swap kit making of series. And before we get any further, I wanted to answer a few of the questions I got on my last video. So I think I need to make it a little more clear what the purpose of this kit is and who it is for. This kit is for someone who maybe has never swapped an engine before and just wants to replace the Rover V8 with an LS as quickly and painlessly as possible in the garage with basic tools over the course of 2, 3, maybe 4 months at most. They don't feel the need to gut the entire drivetrain, replace transmission, replace other things. They just want to fix the only problem, the Rover V8. So hopefully that helps explain some of the decisions behind this kit. I want it to be as plug and play as possible. Hello again. Today's an exciting day because we have a prototype. Oh, as you can see, it is laser cut. Laser cutting is probably not going to be the best long term, but as a prototype, it'll do. The problem with laser cutting is the edge gets a little rough, especially with these thick materials. So our dowel pin holes aren't going to be precise enough. I think for it to be really bulletproof, it'll have to be CNC machined out of billet aluminum. So there's our adapter plate fitted, fits around the LS dowel pins perfectly, clears the LS flex plate beautifully, and it has pre-tapped bolt holes for the Rover bell housing. These LS bell housing bolt holes need to actually be they need to be countersunk because the Rover bell housing will hit the bolts otherwise. So we're gonna have to drill our own countersink. I will go ahead and countersink these holes myself. No big deal. There it is with all the countersinks done. And this is the aftermath of that. There's the plate on top of the Rover bell housing with the dowel pins. One slightly unfortunate thing. So this dowel pin is perfectly lined up, but then this one has a bit of a gap there. I don't know if you see. So my dowel pins are not. These holes are not perfectly lined up, and I was kind of worried about those. For now, I'll probably file the hole bigger and make it fit to continue the prototype, but then I'll have to adjust this before the CNC machined prototype. And that's what that looks like. I'll bolt it up. So yeah, it's on there. So this is the setup I ultimately had to use to find the exact dowel pin locations. Basically, I had to 3D print this piece and nudge the positions over until I got it perfect. So now, with this piece, oh, it's upside down. There we go. Now I have it locking into place. Well, hard to do with one hand, but yeah, it's locking into place on both pins and the center cone I 3D printed. So thanks to that, the whole thing fits perfectly. In the meantime, this just arrived from the laser cutter. A new Reluctor wheel and crankshaft position sensor mount inspired by the Ace kit. So the Reluctor wheel, here's the Ace kit one, and this one that I've reproduced should be identical. And it should fit, let's see, it should fit right over top this new crankshaft pulley. Yep, perfect. So just need to drill and tap holes, countersink, and we're good to go. And then this is our crankshaft position sensor mount, also inspired by the Ace kit. It's supposed to replace this cobbled together thing with this nice mount. That'll go there. And there's our beautiful mount. Let's see how close we got to matching up with the Reluctor wheel. All right, there it is with the new Reluctor wheel. That was very close to perfect. I had to put some washers behind this bolt. Thankfully, I left some wiggle room here to go left and right. That was on purpose. So a few washers behind this bolt, brought it out. Let's see, in alignment with the Reluctor wheel. And then this needs to be spaced way out with some washers or something. Or, and I didn't think of this sooner, I could design the bracket with this up this way. And the reason I didn't is because this bolt was in the way. So I had to put the bend there. But I realized that if I just bend this part and stop my bend, then I could actually fix the bracket. That's a design that I hadn't thought of. So I could look into that. But a few people pointed out to me that, and I agree with them, that this whole setup is one of the more annoying parts of the Ace kit. It's not super reliable because getting the spacing perfect is kind of difficult. And as the engine warms up, I suspect that things kind of warp and it gets out of alignment. And so people get into limp mode because of that. Not to mention it's kind of exposed and it could get damaged. Feels like there's room for improvement. So I know at the very least I have this, but I might look into converting the crankshaft position sensor signal from GM to Rover. So the LS uses a crankshaft Reluctor wheel that's got 24 teeth, and it's completely different from this 58 tooth Reluctor wheel that is more like the Rover one. But with a little computer or something, I should be able to convert the two signals, or just generating a 58 tooth square wave, feeding that into the Rover computer, and then we can get rid of all this, which actually would save costs on the materials and labor for this kit. I've got the Rover bell housing back in here, and next step is to take the engine with the adapter, put it in, and measure for engine mounts. But before I do that, I want to 3D print like a collar for the input shaft, and then double check my dowel pin to center measurements just to be absolutely sure that I got it right. All right, here's what's going on. I put the engine back in. I have the prototype adapter plate in there. The first thing I did is I put on the fan, because with the adapter plate setup, this engine is 1.5 inches forward more so than the Ace kit. So that means that the radiator has to be moved a little bit. Not a ton. Like this seems to be enough right here. Just like 1/2 inch to 1 inch. And everything's good. Everything's good. All right, for engine mount, this is kind of what I'm thinking. Bolt this to the engine. You got this wing that comes out, and we'll put a round bushing under there. Let's see how this fits up. Well, that is actually very close. Only thing is I couldn't bolt it because it's interfering with the exhaust manifold. And then we might have a little bit of a clearance issue with the dipstick. That's easy enough to fix. So while we're figuring out the engine mounts, I thought it might be a good idea to check hood clearance before we commit. So everything's just kind of laid on top roughly, but let's see, because I think I'm sitting a little bit higher than the Ace kit, which would be good for differential clearance and other issues, but will it fit? So we do actually have a bit of a clearance issue, and it's hard to say where the problem is. Maybe it's the intake up here, but you can't see it once you shut. It just won't latch. So I wonder, maybe I put a little grease or something on there to see if it marks the hood. I'll figure out a way. All right, we got some anti-seize on there, and up there's our grease mark. So it was this thing sticking there. And also the map sensor in the back did touch a little. So I kind of like the way the engine is sitting right now, higher than the Ace kit, because that might actually fix the differential hitting the oil pan issue. That, along with the slimmer Holley oil pan. And that was one of the biggest issues with the Ace kit. So to eliminate that would be super valuable. So what I would rather do, rather than lowering the engine, is I would rather start shaving off a little bit off the top of the intake. If all it takes is to chop a 1/2 inch off of that, then I'll just do that, right? Well, after shaving that, I was able to actually latch it, but there was some resistance. So let's see what we're hitting next. there's that chopped off. The hood is clean except for there, which is the map sensor. So if that's the only thing that's hitting, that's good news because that's pretty easy to remedy. You can get some aftermarket map sensors that you can relocate with a little tube or something. So I will go ahead and look into that. I'd rather do that than lower the engine. Anything but lower the engine. Another thing that was hitting was this. It was sticking up, so I just had to clock it down this way. No big deal. So, I mean, with any luck, we might be able to mount the AC low enough that the intake can just go directly above it. We'll see. Well, that's really all it took. I took the map sensor out to test, and there's absolutely no collision anymore. So we get to mount the engine higher. That's awesome. Worth the 5 minutes it took to cut that off. And I'll look into the map sensor relocation. But I heard it's pretty easy, so happy with that. Well, actually, aside from relocating the map sensor, I found that just breaking off the retaining tabs and rotating it to the side, plugging it to the side, should be enough to clear. So, and I read online that it stays in there with broken tabs, no problem. So you don't really need them, I think. Of course, you could use an aftermarket intake that's smoother, flatter, or a car intake. But I'm trying to figure out how to make this work for people. So I've been iterating on these engine mounts for a while now, but where we're at is it's like a 4-piece bracket where these pieces will be welded together. It's like a wing, a solid wing sticking out, and then it's sitting on a puck on like a biscuit engine mount. So that seems to work okay. There's maybe a few details to work out, but I don't know if this is going to be the final design. I made it this far and it's pretty good, but it doesn't fit on the frame mount super well. So I may go for a different style of bushing. We'll see. So here's the next engine mount design I want to experiment with. This would be like a typical cylindrical suspension bushing. This is all welded together, right? And then this on the frame side bolts through the suspension bushings or something like this. So let's see how that goes. It would be nice because it's not a lot of welding. It's pretty simple. The bushings are inexpensive as well, and but also very high quality and very, very effective at isolating vibrations. Meanwhile, I also started looking into the torque converter adapter. So this piece fits snugly around this the bushing, the snout of the torque converter. Bolts to the 4 holes here, and then it brings these up to meet with the GM flex plate. These will be threaded holes. Flex plate bolts into that. The only thing that's missing from this design is I want to integrate the pilot. So there needs to be like a snout or pilot on the torque converter to go into the GM crankshaft. And unfortunately, that can't be made out of aluminum. I'd love to have just milled into this piece, but it needs to be made out of very strong steel, maybe chromoly steel. So I'm thinking of making a separate piece that press fits in here. Maybe it has a flange that it can be bolted down into here as well. That's the thinking. Okay, engine mounts. I have gone through more iterations than I am willing to admit, but I think I finally got something. So, one bent piece like that, one welded piece like that. There's room for the bolts, there's no interference, and then the bushing goes on the frame side. So it'll be like a billet aluminum piece, solid block, with the rubber bushings in here. And that'll go like that, and with a through bolt, and bolted to the frame down there. That'll be a threaded hole. So that is the best solution I have found so far. Let's test fit it. I have applied my hot glue welds. I might add a gusset over here, just to make sure there's no lateral stress on the weld joint. All right, the right side's looking pretty good. That's how that'll fit up. Left side needs a bit of adjustment. I think I went too short, need to go a bit longer. Can't get the bolt to match up here because I need to slide the bracket a little further, but this might be in the way. We'll see. My slot is a little too short too, so let's see if I can make the slot long enough to make this work. So I was still getting a bit suspicious about the position of the dowel pins relative to the center, and I was right to be, because I 3D printed this jig that fits over the input shaft, and this jig is solid, and I was able to put a third dowel pin in the middle, right? That allows me to get more consistent measurements easier. And I used this large protractor and these large pair of calipers to get my measurements. And not saying these are the most precise tools for the purpose, right? It's not a micrometer. Still, I took the measurements over and over again. I was very, very careful, and at least I believe I am close enough with these to be within tolerance. But I was right to be suspicious because the results I got after measuring multiple times were consistent, and they are different than what I have in the CAD. So 157.5 degrees and 184.8 with 185. I know that this pin to the center draws a horizontal line, and then I just have to translate my angle and distances to the CAD, and that'll shift the dowel pin locations a little bit. And if I need to just like shift around all the other bolt holes, basically when the dowel pins shift, I'll match my scanned drawing, I'll match that up to the dowel pins, and if the bolt holes need to shift, those don't need to be so precise, but if they need to shift, I will shift them so that they're closer to where they need to be. So I got my new measurements back in. I actually 3D printed one test already, and I found that the distance should be 185 on each side. And the calipers were misleading me because I was in an awkward spot measuring this one. You can see what I mean. The scan and the pins are out of alignment. So what I'm going to do is I'm going to realign the scan with my hopefully perfect dowel pin positions and then shift everything else to match. And now I have my pattern finalized. You know, another thing I've been concerned about is tolerances. The LS dowel pin needs to come in here and be like a tight fit, but it needs to be able to slide in and out. Meanwhile, the Rover dowel pin, because it slides in and out of the bell housing, I think it should be press fit here. So I'm trying to figure out what the correct sizes and tolerances are to get that effect. And so I picked up a copy of Machinery's Handbook. It's definitely a little overkill, but it's kind of the best book for this sort of thing, because over here it'll tell you the answer to that. It'll say, oh, if you want a running sliding fit, these are the tolerances. Or in our case, for the LS dowel pin, we might want a clearance locational fit, which is it can be assembled or disassembled easily, but it's not press fit. And so you look at your size range. So in our case, we're 0.625, so 0.4 to 0.71. They're class 1, class 2, class 3, etc., which is how tight it is. We probably want like, well, actually, I don't know. I don't know what class we want, but let's say we want a class 2, for example, then we need our hole tolerance to be 0 to 0.7 thousandths of an inch, and our shaft to be 0 to negative 0.4 thousandths of an inch in clearance, in tolerance. So those are the limits. I'm working with a machinist that can maybe help me decipher this and pick the correct tolerance. Well, I think I can finally say I nailed the measurements, because I printed this test piece and it fit perfectly. So turns out, yeah, it was 185 on both sides. Obviously, they used even measurements. They probably designed this whole thing in CAD at Land Rover. So should have known, yeah. that's what it ended up being, and angle of 157.5 degrees. I should have done this from the beginning. Use the input shaft as a reference, and 3 equal dowel pins that I could measure from and grab an angle from. So yeah, I think I got it. So as I mentioned earlier, I'm working with a machinist, and they're waiting on me to finalize my CAD designs. So I need to take some measurements of the distance between the flex plates and the torque converter to see how thick that adapter needs to be. I need to finish adjusting the dowel pins based on my new measurements. Yeah, so I'll show you how I'm going to do that. So this is how I'm going to do it. I'm going to measure this ruler and then zero out my calipers and then place the ruler like this and then use the depth gauge to hit the flex plate. And I got 0.7205 inches. Alright, hopefully you guys can kind of see what I'm doing, but same idea. I'm going to hold the ruler up there. I've got my calipers zeroed out on the ruler. Okay. We're going to use the depth gauge. 1.0345. I'm going to measure a couple times just to be sure. So, checking my notes here. The flex plate is recessed by 0.72 inches and the torque converter is recessed into the bell housing by 1.05. So that means the distance between the flex plate and the torque converter is 1.77 inches, 1 3/4. However, you're supposed to leave a gap between the flex plate and the torque converter. The gap should be 1/8 of an inch to 3/16. And the gap is important because what it does is when you bolt the torque converter up to the flex plate, it pulls the torque converter out of the transmission by 1/8 of an inch to 3/16. That keeps the torque converter from bottoming out into the pump when the flex plate is flexing back and forth. So you need that gap, otherwise you'll damage the transmission. And I think that's something that the ACE kit didn't get quite right. So 1.77 inches is what I said, minus at least 1/8 of an inch. That means the thickness of our torque converter adapter plate needs to be between 1.645 inches and 1.5825. So somewhere in that range. So we'll maybe shoot for the middle. Why not? There's one last thing I forgot to measure, which is the distance between the flex plate mating surface and the crankshaft pilot, because we need to make sure that our pilot adapter goes in here deep enough. I don't know if it needs to go like at least 1/8 of an inch, maybe more. It needs to be able to move in and out. So I think I'm gonna look up what the proper depth is, but I need to know the reference point first. All right, back in CAD again. Down here is a torque converter to flex plate adapter. So 4 bolt holes for the rover torque converter, 3 bolt holes tapped for the flex plates. This little diameter here will fit around the pilot that's on the rover torque converter, and it will center this entire assembly. And then, so that'll all be milled out of aluminum. This will be milled out of chromoly steel, and this will be the pilot that fits into the LS crankshaft. So it's got the radius or the diameter here for the crankshaft, a flange, and a little shoulder here so that it can fit in here precisely and stay centered, and then 4 bolts so that it stays bolted up to that, because this will center our entire torque converter with the crankshaft. So it is super, super important to get this right. And it needs to be chromoly steel because it's going to be in that crankshaft moving back and forth, and you don't want any galling to happen and for this to wear out. So So it needs to be really strong. So I need to get these files ready. It's not enough to just have the 3D model done, but you need to think about the manufacturing and you need to communicate all that very clearly. So I'm working on the drawings. There's going to be a full assembly drawing showing just an overview of everything. And then for each part, in this case 2 parts, I'm going to have detailed drawings with the measurements, the holes that need to be tapped. If there are tolerances that are critical, then I will note those. It's just all the information is going to be here. So, work in progress. Okay, nearly done with the drawings for the torque converter adapter. I ended up adding a bump here. This bump is part of the aluminum side. And the reason I did that is because it allows me to make the chromoly pilot smaller. Otherwise, this snout was kind of long. And because it's going to be made out of chromoly steel, it would be more expensive to produce than the aluminum part. So making it smaller is wiser. And there's really no downside to it. In fact, this bump, we kind of get it for free because the way that that's manufactured is by milling away less material from this block of billet. So we kind of get that for free, and it just makes more sense. So did that. Let's see, the drawings are looking pretty good. I've got the full assembly, the adapter plate with tolerances and tapping and instructions. There's the torque converter snout adapter thing. Now we've got the bell housing adapter plate. This is simpler to do the drawing for. It's just 1 page. All I need to do is specify the tolerances for the dowel pin holes. But otherwise, this is it. Well, I think it's time to wrap up part 2. It's going to be a while until we get the parts back from CNC machining. So in the meantime, I'm going to start on part 3. And hopefully by the time you watch part 3, we'll have the first version of the CNC machine adapters, and we'll probably be working on the power steering and AC compressor adapter, and who knows what else. So stay tuned for that. Thanks for watching.